Welcome to HFCL Time Machine. Past, present, future, all connected.
Let's start with today's chapter, where we explore the invisible physical backbone of our supposedly wireless world, optical fibers.
Right, because, the word wireless is kind of a massive illusion, really.
It totally is. I mean, think about it. When you stream a 4K movie or when you join a video call from your kitchen, you probably think of the internet as this ethereal thing, right? Like it's just floating around in a cloud.
Exactly. But in reality, it's completely physical.
Yeah, it's buried right under the pavement, running through these tiny, incredibly delicate strands of glass.
And, well, the physical scale required to maintain that illusion for you is, frankly, staggering. We tend to just forget that every single wireless connection ultimately ties back into a hardwired subterranean network.
A network that is currently facing a massive bottleneck.
Oh, absolutely. The sheer volume of data moving through that network has triggered basically an infrastructure crisis.
Just to put some numbers to that crisis, how big are we talking?
Well, if you look at the macro context, driven by this massive shift in consumer behavior during the pandemic and skyrocketing mobile data demands, the telecom market value hit $3,048.1 billion US in 2023.
Wow. Over $3 trillion.
Yeah, and we're tracking a 6.0% annual growth rate on that number.
Which sets the stage for the massive physical roadblock we're exploring today. Because we are generating data at an unprecedented rate. I mean, the global fiber optics market alone is projected to reach $9.73 billion by 2027, just to try and handle all of it.
Right, but there's a fundamental problem there.
The Earth isn't getting any bigger.
Exactly.
Yeah.
We're literally running out of underground space to put the pathways that carry this data.
So our mission today is to figure out how we keep scaling the digital world when the physical world is, well, out of room. And specifically, how an engineering marvel HFCL's next-gen microcables is quietly engineering a way out of this bottleneck.
Yeah, because the core conflict here is insatiable data demand meeting immovable physical reality.
Right.
To service more subscribers with faster speeds, network operators basically need cables with a higher fiber count. And historically, if you want more fiber, you just build a wider cable.
Which makes sense, logically.
Right. But the underground duct infrastructure, the literal plastic pipes buried under our cities, is completely finite.
Okay, let's unpack this, because to a layperson, it feels like we're just trying to force a massive fire hose of data through, like, an underground garden hose.
That is a perfect analogy, actually.
So if we need high-capacity networks, why are we artificially limiting ourselves? I mean, why not just dig a bigger trench and lay standard, thicker optical cables?
Well, digging is actually the single most expensive and contentious part of telecommunications.
Really? Just moving the dirt.
Oh, yeah. Expanding existing duct networks involves tearing up city streets, disrupting traffic, and navigating this entire bureaucratic nightmare of getting approvals from local authorities.
Oh, I see. So it's not just the labor, it's the red tape.
Exactly. You're talking about months of civil engineering work for a single city block. It is a logistical and financial quagmire that operators desperately want to avoid, so they have to use the existing pipes.
Okay, so you're a network operator staring down at a crowded plastic tube that's already mostly full of old cables. I imagine if you try to forcefully stuff a thick conventional cable into whatever space is left, you're going to run into severe issues.
Massive issues.
Yeah.
Especially when you hit the subscriber loop.
The subscriber loop?
Yeah, that's where the nightmare really begins. It's that last mile connection branching off the main street and going directly into a home or an office building.
And I'm guessing that's never a straight, easy line.
Never. You have tight bends, 90-degree corners, super awkward angles. Traditional, thicker optical cables are rigid.
Right.
So forcing a thick cable around a tight corner doesn't just risk breaking it physically, it fundamentally breaks the physics of how the data travels, causing massive signal degradation.
Let me see if I have the physics right here. Because light travels down these glass threads using total internal reflection, right? Like it bounces off the inner walls of the fiber.
Exactly.
But if you bend a rigid cable too sharply, you change the angle of that bounce.
Right. The light literally hits the boundary at the wrong angle and just escapes the core of the fiber entirely.
Oh, wow.
Yeah, it leaks out into the surrounding material. And when the light escapes, your data drops. This raises an important question. How do you exponentially increase network capacity when you are trapped by extreme constraints in duct space, length, and geometry.
Because conventional thick cables just completely fail the geometry test.
Exactly.
So if digging bigger holes bankrupts the operator and stuffing thick cables into tight corners ruins the signal, the only move left on the board is to just shrink the cables themselves.
That's the only way forward.
But we're talking about incredibly vital infrastructure carrying the entire global economy. And glass threads are inherently brittle. If I bend a thin piece of glass, it shatters. I just struggle to understand how miniaturizing a glass cable doesn't just create an incredibly fragile liability.
It feels completely counterintuitive, doesn't it?
Yep.
You would absolutely expect a microcable to just snap under the slightest tension.
Yeah.
But the resilience comes from an absolute masterclass in material science, not just, making the glass smaller. Let's look at the baseline anatomy of a microcable.
Okay.
They typically cap out at about 12 millimeters in diameter. And at the absolute center, you have the telecommunications-grade optical fibers transmitting the light.
But you can't just leave bare glass rubbing against bare glass when a cable twists, right? There has to be some sort of buffer.
Definitely. The primary defense is the coating on the individual fibers. Standard industry applications use a 250 micrometer coating of an acrylate thermoset material.
Okay.
But for high-density applications where space is super critical, engineers actually thin that coating down to 200 micrometers.
To visualize that scale for you guys listening, a single strand of human hair is roughly 70 to 100 micrometers thick.
Right.
So the glass fiber plus its protective coating is barely the thickness of 2 or 3 human hairs.
It's remarkably tiny.
But what makes that specific acrylate thermoset material so special? I mean, why not just use normal plastic?
Well, thermoset plastics, unlike typical plastics that melt when they get hot, undergo a chemical cross-linking process when they cure.
Oh, interesting.
Yeah, so once they are set, they form this incredibly stable, rigid, microscopic structural shield around the glass that simply won't deform under extreme temperatures. It locks the delicate glass core into a protective state.
So you have these thermoset-coated strands of glass. I imagine you bundle them up to form the actual cable.
You bundle them, yeah, but then you surround them with specific buffering materials.
Like what?
Think of it as a microscopic shock absorber system. These buffers absorb lateral crushing forces and physical stress, basically isolating the delicate glass from the mechanical forces applied to the outside of the cable.
Okay, that makes sense.
And finally, you wrap the entire bundle in a protective outer sheath.
And from what I read in the research, these sheaths are highly specialized depending on the environment. It's not just basic rubber wrapping.
Bad at all.
They use polyethylene for intense moisture protection or PVC for flexibility.
Yeah.
I also saw LSCH mentioned heavily, low smoke, zero halogen.
Which is an absolute necessity for modern indoor or subterranean infrastructure.
Why is that?
If a fire breaks out in a building or, say, a subway tunnel, standard plastics burn and release toxic, highly corrosive halogen gases.
Oh, that sounds awful.
It is. LSCH sheaths are chemically formulated to prevent that, protecting both human life and the surrounding electronic equipment during a fire.
So we have this microscopic body armor protecting the glass, and despite shrinking everything down, operators don't have to invent new ways to plug them in, right?
No, not at all. You can still use standard fusion splicing, melting the glass ends together perfectly, or just use regular field connectors.
So they engineered the miniaturization while strictly maintaining the legacy performance ratings. Tensile strength, attenuation limits, they all still meet the industry standards.
Exactly.
Here's where it gets really interesting because the standard 12-millimeter microcable is an incredible feat of engineering on its own.
Sure is.
But HFCL looked at the current global data demands and decided 12 millimeters was still entirely too fat.
Yeah, they really did.
They pushed the physics of miniaturization to an absolute bleeding edge with a new family of ultra-compact microcable utilizing that 200 micrometer fiber we just talked about.
We are definitely moving past incremental updates here. HFCL achieved a radical leap in packaging density.
The specification that really jumps off the page in their white paper is their 288 fiber nano-thin variant.
Right, the ManoFin.
They managed to pack 288 individual optical fibers into a single cable that is a mere 7.4 millimeters in diameter.
Which achieves a packaging density of 6.7 fibers per square millimeter.
That's wild.
For context, a conventional 200 micrometer cable carrying that exact same payload of 288 fibers typically measures around 8.1 millimeters thick.
Now, I have to assume some people listening are thinking, we're talking about a difference of 0.7 millimeters. That is a fraction of an inch. Why is shaving less than a millimeter off a cable considered a game-changing operational victory for a network operator?
Because volumetric efficiency compounds over distance.
Okay, what do you mean by that?
Well, when you are deploying hundreds of kilometers of cable through thousands of underground ducts, that fractional reduction in the cross-sectional area opens up enormous amounts of physical space in the infrastructure.
Ah,
It allows operators to run multiple 7.4 millimeter cables in a conduit that could previously only hold one conventional cable. You are literally multiplying the data capacity of a city block without digging a single trench.
that is a huge deal. And it isn't just some fragile lab experiment either. The thermal resilience specs are wild.
Oh yeah, they are.
HFCL engineered these to operate flawlessly from negative 40 degrees Celsius all the way up to positive 70 degrees Celsius. You can bury this stuff under the ice in Alaska or under the sand in Dubai, and the structural integrity holds.
And beyond the thermal resilience, what's fascinating here is how they solve the legacy compatibility puzzle.
Right, because you're rarely building a network entirely from scratch.
Exactly. You are almost always splicing brand new cables into infrastructure that was buried like 20 years ago.
And if your brand new ultra-thin fiber doesn't match the older, thicker fiber perfectly, you have a major bottleneck.
You do. So HFCL utilizes an ITU-T compliant G.657.A1 fiber.
Okay, that's a lot of letters and numbers.
Yeah, but the critical metric here is something called the mode field diameter,
Yeah.
which sits at a nominal 9.1 micrometers.
So the mode field diameter is essentially the width of the actual light beam traveling down the center of the fiber.
Correct.
Let me make sure I'm visualizing this correctly. If you try to splice a modern fiber with a 9 micrometer light beam into an old fiber built for an 11 micrometer beam, you basically create a microscopic lip at the connection point.
Yes.
The light hits that lip, scatters, and you lose your data.
It creates an immediate point of failure. But by engineering the 9.1 micrometer mode field diameter, HXCL's new fiber perfectly matches the light profile of the massive installed base of older legacy fibers.
The ones known as G652.E networks.
Exactly. This allows for incredibly low-loss splicing between the new and the old. The industry relies on this for what we call first-time right, or FTR installation.
Let me challenge this economic angle, though. You talk about FTR saving operators massive headaches.
Sure.
But researching and engineering a highly specialized 7.4 millimeter thermoset-coated legacy matching glass cable has to require incredible upfront R&D and manufacturing costs.
It does.
Does this actually save an operator money at the end of the day, or is it just an engineering flex?
Well, the material cost of the cable is actually a fraction of the total deployment cost.
Really?
Yeah, the real expense in telecommunications is labor. Paying highly specialized technicians to descend into a muddy trench and fuse microscopic glass under a microscope costs an absolute fortune by the hour.
Oh, right.
If a splice fails because the light beam wicks don't match, that technician has to cut the cable, prep it, and do it all over again. Or worse, the flaw isn't discovered until they leave, requiring another truck roll to go back and fix it.
Which is wildly expensive.
Enabling first-time right installation
Yeah.
drastically slashes the largest line item on an operator's budget.
That makes a lot of sense.
Yeah.
Labor is the true bottleneck. But, that brings up an even bigger mechanical mystery.
What's that?
We've established that the 7.4 millimeter cable is incredibly dense, but it's physically delicate compared to heavy-duty traditional cables. Getting it into the ground seems terrifying.
It can be.
Like if you tie a winch to a cable that thin and yank it through a mile of twisting underground plastic tube, the friction alone would just stretch the glass inside until it snaps, wouldn't it?
Oh, absolutely. Pulling tension is the ultimate enemy of optical glass.
Yeah.
If you drag it, friction compounds exponentially with every meter and every slight bend in the pipe. Eventually, it just destroys the fiber cores. So modern installation bypasses pulling entirely using a technique called air-blown or jetting installation.
Okay, I have to stop you there. Air blown.
Yeah,
Wait, they don't just pull these through the dirt with a truck, they blow them through pipes with air.
they do. And HFCL's nano-thin cables are purpose-built for this exact method.
How does an air compressor move a dense multi-kilometer glass cable?
Well, think of the physics behind an air hockey table.
Okay.
If you push a plastic puck across bare wood, the friction stops it almost immediately, right?
Sure.
But when you force high-pressure air through the tiny holes in the table, the air pressure creates a microcushion. The puck essentially floats, completely removing the surface friction. Jetting works on the exact same principle, but inside a tube.
So they pump high-pressure air continuously into the microduct, And it acts as a fluid cushion all the way around the cable, lifting it away from the walls of the pipe.
Exactly. The airflow carries the cable forward while suspending it, which practically eliminates the mechanical pulling tension that would normally shatter the glass.
That is brilliant.
And HFCL's white paper highlights that their cables are blow-optimized with the specific structural stiffness and a UV-stabilized low-friction outer jacket.
And what does that do for the speed?
By shrinking the diameter to 7.4 millimeters and optimizing the jacket's texture, they increase the jetting speed by up to 29% compared to conventional 200 micrometer cables.
Wow. And the performance data they published from the IEC E24 track test, which is, a brutal industry standard gauntlet for cables, is just astounding.
It really is.
They took that 288 fiber nano-thin cable and successfully jetted it a distance of 2 kilometers into a 1410 millimeter microduct.
Right.
Meaning the duct has a 14 millimeter outer diameter and a 10 millimeter inner diameter. And they pushed it 2 kilometers at an average speed of 54 meters per minute.
Yeah, moving 54 meters per minute through a conduit that tight without damaging a single microscopic strand of glass completely redefines the speed at which a city can upgrade its infrastructure.
So what does this all mean holistically? Moving fast is great, but beyond just the speed of installation, what is the actual ripple effect of deploying a 7.4 millimeter air-blown cable?
Well, it creates a domino effect of efficiencies across logistics, human impact, and even the environmental footprint.
Let's start with logistics.
Logistically, a 7.4 millimeter cable obviously takes up significantly less physical volume. So you can wind vastly more kilometers of cable onto a much smaller drum.
Right.
Smaller drums mean you need fewer heavy-duty transport trucks on the road, taking up less warehouse space, and simplifying navigation through congested urban environments.
And I imagine a smaller drum fundamentally changes an installation crew's day-to-day operations, too.
Oh, drastically.
Huh.
It reduces the physical toll on the crews. Maneuvering massive, heavy wooden spools of traditional cable is, incredibly dangerous.
Yeah, I bet.
Smaller, lighter drums mean fewer workplace injuries, less physical fatigue, and much faster setup times.
Honestly, I think the most overlooked benefit is the environmental impact.
Absolutely.
By utilizing these microcables that just slide effortlessly into existing smaller conduits, you bypass the need for extensive civil groundwork entirely.
Which is huge.
You aren't running heavy diesel excavators for weeks to dig open trenches. You aren't consuming thousands of tons of raw materials to manufacture massive new plastic ducts. The carbon footprint of the entire deployment just drops off a cliff.
It's a compounding benefit model. You dramatically cut plastic usage, diesel fuel, and physical labor, and the reward is a faster, more resilient internet.
Win-win.
Which is exactly why regions around the world are aggressively leaning into this specific technology to execute their digital policy goals. This isn't just a niche engineering problem, it's a global race.
It really is. Looking at the geographical breakdown, the demand is surging universally. In 2022, the Asia-Pacific region dominated the wire and cable industry, capturing a massive 37.4% of the revenue share.
That's a huge slice.
But the push for connectivity is reshaping every major market.
If we connect this to the bigger picture, each region has a distinct catalyst driving this urgency.
Like in North America.
In North America, telecom giants are basically scrambling to fortify fiber networks just to stay ahead of the sheer raw data consumption by consumers streaming and utilizing cloud services.
And Europe.
In Europe, the pressure is largely regulatory. They are racing against the clock to meet the digital agendas for Europe 2025, which mandate substantial continent-wide infrastructure growth.
And then you have India, where the market expansion is absolutely explosive. It's heavily incentivized by national frameworks like the Make in India initiative and Go Green policies.
Right.
Policies that prioritize exactly the kind of eco-friendly, high-density infrastructure HFCL is building.
And HFCL's role here extends far beyond just manufacturing wire. Operating as a global tech company, they are delivering the fundamental building blocks required for scalable, point-to-point, and point-to-multipoint architectures.
Because you can't just mandate connectivity. Right?
You cannot bridge the global digital divide with policy alone. You need cost-effective, sustainable physical pathways to actually connect those billions of people.
It fundamentally changes how we interact with our infrastructure. By shrinking our physical connections, we are unlocking virtually infinite expansion for our digital worlds.
It's quite a paradox, but it's true.
But this does leave me with a lingering thought about the future. If we've managed to engineer silica glass down to 7.4 millimeters to house 288 individual optical fibers, we are rapidly approaching the physical limits of the material itself.
We really are.
You can only make glass so thin before the physics of light break down. Will the next leap in data transmission require abandoning solid glass entirely?
That's the big question.
I mean, researchers are already experimenting with hollow core fibers, literally beaming data lasers through empty air trapped inside a microscopic honeycomb structure just to bypass the latency of solid glass. Just how much further can we push the physical world to serve the digital one?
It's going to be fascinating to watch.
And that brings us to the end of this chapter in the HFCL time machine. Until next time, stay connected to what's next.
You've been listening to HFCL Time Machine. For more conversations like this, find us on LinkedIn, Instagram, and YouTube.